Assalamualaikum dear students. This is our next problem. Problem once again having been chosen from the book Modern Physics by Kenneth S. Crane. This problem is again about stopping potential and wavelength. Okay. Our last two problems were also on the same topic. Okay. So in this video we will have to work less because we have already worked enough on this topic in previous two videos or previous two problems. As usual, we first come towards this statement. A surface of zinc is illuminated and photoelectrons are observed. Part A of this problem says what is the largest wavelength that will cause photoelectrons to be emitted. Part B of this problem says what is the stopping potential when light of wavelength 22.0 nanometer is used. Okay, in part A we have to find the largest wavelength, and in part B we have to find the stopping potential while wavelength is given 220 nanometer. Okay, now students, we move towards solution, but before moving towards its solution in a proper manner, as usual we first come to toolkit. So among tools, tool number 1 is that table which has already been taken many times in our previous problems. Okay. So in this table, speed of light is given and value of Planck's constant h is given. Value of Planck's constant h is not only given in terms of joule second but also in terms of electron volt dot second. Okay. Now we move towards this is actually tool number previous was tool number 1 and this is actually tool number 2. This needs to be rectified. Okay, yes. Tool number 1 is table which has already been chosen many times. Okay, and tool number 2, in tool number 2 work functions of various materials have been shown or given. Okay, tool number 2 shows a list of work functions of various materials in which zinc is also included. Okay, Zn 1 2 3 4 5. Okay, at serial number 5 or row number 5, fifth row, zinc having work function 4.31 electron volt, okay, which is denoted by phi, is also given. Okay, in our previous problem we had also shown a table in which various Greek alphabets were shown so that we may ensure that we are pronouncing this constant correctly. Okay, so this constant was written as phi, meaning phi, and another similar constant was psi, psi. Okay, but that psi was very enough different from this Greek alphabet symbol there. Okay, this is phi. Okay, so work function phi of zinc Zn is 4.31 electron volt. Now we come toward the solution. Part A, we know that cutoff wavelength is given as lambda c, where lambda usually denotes wavelength and c is here written as a subscript of lambda, meaning cutoff wavelength. Cutoff wavelength lambda c is equal to hc over phi, that is Planck's constant into speed of light divided by work function of zinc. Dear students, all these three values have been given in our problem. Okay, two values in the numerator are given in the table, that is which we introduced as a tool number 1, and value of work function of zinc is given in tool number 2. Okay, so all these three values are given, and when we will put these three values and simplify, we will get cutoff wavelength lambda c equal to this over this. Okay, second will be cancelled out with the second, electron volt will be cancelled out with electron volt, and we will be left only with meter. Okay, so its answer will become cutoff wavelength lambda c equal to 2.88 into 10 to power minus 7 meter. But dear students, as I have mentioned previously, that just as a fashion or a formality, 10 to power minus 7 is not appropriate for us. Okay, what is appropriate for us is either 10 to power minus 6 or 10 to power minus 9 or 10 to power minus 12. Okay, that is to say differences of multiples of 10 raised to the power 3. Okay, 10 to power 3 or minus 3, 10 to power 6 or minus 6, 10 to power 9 or minus 9, 10 to power 12 or minus 12, 10 to power 15 or minus 15, 10 to power 18 or minus 18, 10 to power 21 or minus 21, 10 to power 24 or minus 24x. Okay, so dear students, in order to convert this 10 to power minus 7 into 10 to power minus 9, this decimal will be shifted 2 stages ahead. Okay, that is, instead, in place of 2.88, it will become 288. Okay, this value will take the form as 288 into 10 to power minus 9 meter, and we know that 10 to power minus 9 is called nano, denoted by n. So this is equal to 288 nanometer nm. Okay, now we come towards part B. Okay, part B, we know that maximum kinetic energy of photoelectrons is given by K max. K denotes kinetic energy and max standing for maximum. Maximum kinetic energy is equal to EVS, where Vs is stopping potential, and this is alternatively equal to, by definition, Hf minus work function phi. Okay, here dear students, we know that frequency and wavelength lambda are reciprocal of each other along with the involvement of speed of light c. That is, f is equal to c over lambda, and lambda is equal to c over f. Okay, wavelength lambda and frequency f are reciprocal of each other along with the involvement of speed of light c. Okay, so maximum kinetic energy K max has become equal to hc over lambda minus work function phi. Okay, here dear students, we will not take K max. Okay, this is only by definition. we will here use its equivalent value. Okay, that is EVS is equal to HC over lambda minus phi, where Vs is the stopping potential. Okay, so this implies that EVS becomes equal to HC. Both these values have been given in tool number 1. Moreover, value of lambda is given in the problem. Okay, 220 nanometer. Okay, minus work function phi, which we have which we have not calculated. It is also given in the table. Okay, 4.31 zinc. We had shown in tool number 2 a table of work functions of various materials, in which work function of zinc was also given. Okay, so because these two quantities are in the shape of a numerator and denominator, so minus value of work function phi will also be written in this form. Okay, in the denominator unity 1 will be assumed. Okay, so when we will simplify it, second will be cancelled out with second. Okay, meter will be cancelled out with meter, and we will be left with only electron volt. Okay, so we will get 5.63 electron volt minus 4.31 electron volt. Both are electron volt. Okay, so in other words, simply we can say that we can take electron volt as common, and then within bracket 5.63 minus 4.31, and this will become equal to 1.32 electron volt EV. What is this? This is equal to EVS. Okay, EVS is equal to 1.32 EV. When we will divide both sides by E, then E will be eliminated, and we will get Vs equal to 1.32 V. Okay, this was value of EVS, but we are concerned with the value of only Vs, stopping potential. So what we will do, we will divide both sides of this equation by E, and in this way E will be eliminated and only Vs will be left on left side, and its alternate value will be left on right side, which is 1.32 volt. And this is the end of our problem. Till next problem.